Okay, MacMaths, let's do some maths today. Part E, blocks on people in a scale pan or lift. Okay, so that's what we're doing today. So I'm going to cover this one. So there it is. It was always my nightmare, this question. And this is what this is a favourite, by the way, the one I've made up here. So yeah, good luck when you see this one on the exam, but it does crop up. You'll see it in all of the textbooks as well. So they call a scale pan this light, they'll describe it as a light. In other words, it has no mass. You know, obviously it has a mass, but at light you say that the mass is negligible. So just this sort of rod and a couple of strings, and then it's being like lifted up, sort of like winching something up out of a well. And made it more difficult, this one, and you'll see these in the textbooks as well, is a block on a scale pan. Okay, and you're asked to find the tension. Okay, so this is the rope that's pulling it up. Okay, so the tension in there, and the force exerted of A on B as it's moving, and the force exerted of B on the pan as the pan is moving up. Okay, so that's what we're going to go through today. Okay, so let's start with this one. So I'll do this in red and find the tension. Okay, so this is light, so we're going to assume it has no mass for the purposes of this model. And these are two strings here, just like strings. Okay, so they'll have a tension, but it's all symmetrical, so they'll be connected to the tension of this one, but we just want a tension in the main rope. Okay. So first of all, let's have a look at that. Treating it as a whole thing. So the whole thing, first of all, just got to be careful. SI units, we use kilograms. So 500 grams is the weight of the whole thing. Sorry, 500 grams is the mass of the whole thing. That's 0.5 kilograms. Okay, so the mass is 0.5 kilograms. And we're going to go F equals ma. The force then, so this is considering the whole thing, so the force is the tension pulling it up minus, and it is moving up by an acceleration of 0.4 meters per second, and the force acting opposite to that, pulling it down, is 0.5 g, isn't it? Okay, so mass times gravity, that's the weight of the pan. So this force is obviously bigger than that force, so the net force, so that's why it's moving up, so the net force is equal to the mass, which is 0.5, the whole thing, times the acceleration, which we know, which is 0.4. Okay, and 0.5 g is 0.5 of 9.8, so we've got t minus 4.9 is equal to that times that, of course, is 0.2. Okay, and we add 4.9 to both sides to get 5.1 newtons. There we go, and that's the tension in the string pulling the scale pan up. The force exerted, next part, force exerted of A on B. Ooh, let's label these A and B. Sorry, forgot to label those. If you get this, the force exerted from A on B is the same, you know, when they're on each other and they're moving, the force exerted of one on the other is the same whichever way. So B onto A into B is the same thing. So just pick the easiest one. I'm going to consider just A. So if I just consider A, what's happening to A? So A has it has a mass of 0.1 kilograms. It's got a force acting down, and that force is mg, its weight times gravity, and it's got a force acting up, and that's the force of B pushing it up, and it's got an acceleration, hasn't it, of 0.4 meters per second on this pan. Okay, so because it's going up, this is the force, the overriding force. So the net force, of course, is this force that B is putting on it, pushing it up, minus the mg of the weight of the block is equal to the mass times the acceleration. There's my F equals ma, my net force. So this B minus 0.1 times 9.8 is equal to the mass, which is 0.1 times 0. Acceleration is 0.4, isn't it? Okay, so we've got that. I've done that wrong on mine before. Okay, so when we do that, we've got that is going to be 0.04. 0.1 times that is going to be 0.98. So adding those two together is going to give me 1.02, isn't it? Adding that to both sides, newtons. So that is the force exerted by A on B or B on A. It's the same thing. Okay, so it's a force between the two of 1.02 newtons. The force exerted, you know, I always struggled with these ones here. The force exerted by B on the pan, you can do it sort of two ways if you want. You can look at if the first way is to look at this acting down, what's the weight of this? So that acting down on the pan is 0.5, isn't it? That's acting down on the pan. And what force of the pan is acting up to move the whole thing at 0.4 meters per second? Okay, so we can go the force acting up minus the force acting down, which is 0.5 g, is equal to the mass of this, which is 0.5 times the acceleration. You'll see it's the same as this equation here, and so that force is 5.1 newtons. So we can do it that way. The book considers the actual pan itself. Okay, so the pan itself has got a it has a force of 5.1, doesn't it, newtons acting on it, because that's, we've already worked that out, that's the tension. That is and minus the force of B acting down on it, which contains A as well. So we've got the force of the pan pushing up minus the force acting down is equal to the mass times acceleration. Now the force acting up, of course, is the 5.1 newtons, because we've worked that out, and the force acting down, the force of B and A on top of that, and the mass of the pan, you know, is 0 times the acceleration. So you get a 0 doing it that way, so you get 5.1 minus B, and so B is obviously equal to 5.1 sort of newtons doing it that way. The force acting of B down, or, you know, or the pan on B, you know, is 5.1 newtons. So there's a couple of different ways of looking at that one. Okay, now I hope that one's okay. It's my least favourite. I hate sort of trying to think about it. I've had lots of conversations with my colleagues about those sorts of questions when I have to teach it and get my mind around it. You know, blocks on blocks moving. It's my worst nightmare, really. I know it's only simple, but I don't like it. I can always work it out, but by thinking about it and thinking about the forces. But it's one of those things that I find it more difficult to explain. I hope that's okay. I have got you. You get that? That's a very common question. It's a lot easier if it's just one block on the pan. So I've got you a question to do. So have a go at this question, and then put it on pause. You know, put it on pause. Read the question, put it on pause, and then watch the video. So this is a man of 80 kilograms stands in a lift of mass 500 kilograms. The lift accelerates up, is pulled up by a steel cable. The acceleration is that. Find the tension in the cable, the force exerted, the lift on the man, or the man on the lift. And then later on, the lift's going down. So you've got the same thing going down at the same acceleration. It's accelerating down. The man's still inside. Find the new tension and the force exerted by the lift on the man then. Okay, so those forces change. Put on pause, have a go at those. Okay, right, so you've had a go at this. I hope you've drawn a nice diagram. So I'm going to draw a nice diagram. Just going to move that. Can I just don't want that to be out your sight there. There we go. And I'm going to draw this here. Make sure that's in shot. It is. And the man in it. There it is. And let's do the first part. So there's a tension in that. It's moving up, isn't it? 0.6 meters per second to the -1. And yeah, so there we go. And what's the man? Sorry, the man is 80 kilograms. 80 kilograms. And the lift is 500 kilograms. Let's write that in there. Okay. So, if we do A for this first part, considering the whole thing, F equals ma, so it's moving up. So the net force, of course, is the net force is the tension pulling it up in the string minus the total weight, which is 580 kilograms times g, isn't it? That's the weight of that. The mass times gravity is equal to the mass, which is 580, times acceleration is 0.6. So multiplying it all out, you get T is equal to, that is 348, plus your 580G, so that times 9.8, and you work it all out, okay, on your calculator, and it's 6032 newtons. So that's the tension. If we just consider man for the second one, the force exerted by the lift on the man. So I'm going to look at the man. So the man, there he is, as the floor of the lift, and he's got a mass of 80G acting down. So there is that lift is putting a force on him, isn't it? It's pushing him up, and it's greater than his force down. So considering the man and the floor of the lift, so if I go F equals ma, that force is the leading force because it's going up. So I've got F minus 80G is equal to the mass of the man, which is 80 times his acceleration, 0.6. So I'm considering the force is acting on the man. So 80G is acting down his weight, and a force is pushing him up that's bigger than 80, which is why he's moving him up. So if I do that, 6, 8, 48, so that is that right? Yeah, 48 plus 80G, and the force acting on him would be 832 newtons. Okay, so that's the force of the lift acting on the man, or the man acting on the lift. Okay, so there we go. That's just one block in a lift. There is a second part to this. This is later on. It all goes pear-shaped, starts accelerating down. Oh no, 0.6 the same, sorry. Let's move that down. What happens when it's accelerating down? Still going to be tension. Okay. So let's have a look at this now. So when it's acting down, so A again, the tension in the string. This here now, the force is acting down on more than the tension needs to be in the string. So the forces of the lift and the man, that force is greater than the tension in the string. If they were equal, the mechanics of the mechanics of the lift shaft is they make the tension equal to the weight of the occupants and the lift to have it stationary, to have it still. Okay, and then they release that tension to let it start to move down, so they make this less than the actual weight of the lift and the people in it, and then it starts to move down. That's how it works. Okay, so we've got F equals ma again. So this is the overriding force, so we've got 580g minus the tension in the string is equal to the mass, of course, which is 580, times the acceleration, and we're going down is positive now, which is 0.6. Okay, so we've got that as the positive direction, so that it's minus t because that's going the opposite way. So that's our equation to solve now. So this time we've got to move the t over that 0.6, so we end up with being t is equal to 580g minus 580 times 0.6, and if we do that we get t, if you work it out, that's 348, and take that away from that, and that will be 5336 newtons. Okay, quite a lot, because of course 580 times 9.8, you're looking at close to 5,800, aren't you? Newtons there. Okay, so that's the tension in the string now. You can see the tension in the string is less than it was when it's pulling it up. It has to be less than the weight acting down, otherwise it would move in the opposite direction. And again, if we do the same thing here, the man on the lift, so your part B, so there he is, he's got his 80g acting down. The force acting up now is not going to be as much, is it? So otherwise it would move up. So you've got your 0.6 acting down there. So now we're at F equals ma. This is the leading force. So you've got your 80g minus the force is equal to his mass, which is 80, times acceleration, which is 0.6. So that's 48. That over to there, that over to there. So you've got the force is equal to 80g minus 48, just rearranging that. I've been a bit naughty, haven't I? 80g minus f, doing that quickly. Okay, I am a trained professional. And so 80 times 9.8 minus 48 gives you a force of 736 newtons. Okay, so that's the last one where you get people stood in lifts, moving lifts up, going up and down. And I tried to think of an example where the lift is moving up or the lift is moving down. Okay, and considering the forces involved. Hope that makes sense. Okay.